So now that we know what a partial derivative tells us, right, it tells us the slope of a tangent line that we would get to the graph of our multivariable function if we were to first slice that graph in a vertical plane to obtain a trace. So in our previous activity, we had slices of the graph of this function of two variables, xy squared over x plus 1. And when we took a slice in the vertical plane with a constant value of y, we got a trace that looked like this, and the slope of its tangent line was positive 1 at the marked point. If we took a slice in the plane x equals 1, so in a plane that's parallel to the yz plane, we got a slice that looked like this. It had equation y squared over 2, z equals y squared over 2, and so at this marked point, the slope of that tangent line was equal to 2. And so if we put all of this stuff back into context, here is a graph of the full multivariable function xy squared over x plus 1, and there are those two traces. So here is the xz trace that you found in the first part of the problem, and a slope of its tangent line at the marked point right here would be 1. So in the xz direction, the slope of that tangent line would be equal to 1. Whereas in the y direction, if we look at the slice that we would take in the y direction, at that point, it looks like this parabola, y squared over 2. Whoops, looking at it from the back side here. Here it is from the front side. And so a slope of the tangent line to the graph at that point would be equal to 2. And so we're just kind of seeing these two slices, right? The slice that's just in the x direction with a constant value of y, and a slice in just the y direction at a constant value of x. And each one of those has its own derivative, its own slope of a tangent line associated with it. So how do we take that understanding of what partial derivatives tell us and come up with a way of actually computing partial derivatives without having to go through that whole process of substituting a specific value for one of the variables in the way? So the way to do that is just to play a game of pretend with ourselves, right? If I want to compute the x partial derivative of a multivariable function, then what I ought to do is, if that function has other variables inside of it that are used to represent its definition, I'm just going to pretend that those other variables are constants. So those other variables should act like constants do when we take an x partial derivative. Y should act like a constant. If I take a y partial derivative, then x should act like a constant. And so it does require a little bit of, I like to call it a suspension of disbelief in a way. That if we just look, for example, at this first part of this next activity, let's just do this first one together, and then I want to turn you loose with your teams on parts B, C, and D. So we start with a multivariable function, f of x and y is 3x to the power 3 minus 2x squared y to the 5th. And our job is to find the x partial derivative, a formula for the x partial derivative of that function, as well as a formula for the y partial derivative of that function. So just to kind of recap, when we take a partial derivative using just algebra without having to think about the traces the whole time, we are doing a process of sort of convincing ourselves, believing temporarily, that every variable except for the one that we're taking the derivative with respect to behaves like a constant. So if I'm taking the x partial derivative and I look at this original function, this first term, 3x to the power 3, is a variable term. And the second term, 2x squared y to the 5th, is also a variable term, but the y to the 5th part of that variable term is going to behave like a constant. And so from the point of view of its derivative, that 2y to the 5th is just going to come along for the ride, and the derivative is just going to impact this x squared factor, which turns it into a 2x. Similarly, but with a shoe on the other foot, when y is my variable and I'm finding the y partial derivative, then x needs to be treated like a constant. And in that perspective, this entire first term, 3x to the power 3, is a constant in the y perspective. And so its derivative with respect to y is just 0. Similarly, this 2x squared is a now constant multiple attached to this y to the 5th. And so the derivative of 2x squared y to the 5th with respect to y is 2x squared times the derivative of y to the 5th, which is 5y to the 4th. And then we simplify that out. So that's our sort of first exposure to how can we use this idea behind how we interpret a partial derivative to actually help us to compute a partial derivative. And so your task with your team over the next couple of minutes, let's set aside maybe 10 minutes for this, because you're probably going to need to pull out some of your old derivative rules from single variable calculus to navigate your way through these. But find the x and y partial derivatives of this function in part B, as well as the r and s partial derivatives of this function in part C. So let's do parts B and C before we come back together and tackle part D together. So you got some good practice with partial derivatives, again, sort of suspending that disbelief that all but one of the variables behaves like a constant when you take a partial derivative, and only the variable that you're interested in is the one that sort of gets treated like it's a variable in a single variable calculus sense. So the first parts A, B, and C deal with functions of 2 variables. In part D, you had the opportunity to work with a function of 3 variables, and the only real difference, right, is that, for example, when I take a W partial derivative of this function, I need to pretend that X and Y both behave like constants. And so as I was hearing your team sort of talk through this, you notice that with respect to W, this entire cosine of 3x squared plus 4xy cubed plus y, that whole chunk all behaves like a constant. Right? So when you took the derivative of that, it's really 6w plus 1 quantity multiplied by a constant. And so its derivative just ends up being 6 times that big constant over there. Great, and then part E is the same kind of deal. Since it's just like part D, let's skip it for now. But if you ever want to get some more practice with quotient rule and taking the derivative of exponential functions that have a base that's not E, feel free to come back to that one later.